Today we're covering Chapter 13, or Remote Connectivity. This chapter, it's got a lot of definitions in it. So the first one's multiplexer. You'll see this abbreviated MUX at time. MUX. And this is a device that takes a single circuit and combines it with other circuits on a single wire. And then the reverse is a demultiplexer, and this one splits out individual circuits from a multiplex line. So a lot of times we'll have sorry about that. So you may have a bunch of locations out here that you're coming in facilities. They take these through these and they might be called T1 or E1 circuits or something like that, T3s. And they come down here to this MUX, and from there they're all combined on this one circuit until they get to, what's called a central office. So that's kind of how a multiplexer is taking all these lines from different buildings, different companies. They put them all together. This is located in a central office of a telephone company. Put them all together. They trunk them into a cable, and they send that from central office to central office. And in the other central office, they can also run through a demux process, where the circuits now go back out to different facilities. The local exchange is a group of individual public circuits that are served by a single multiplexer. A central office this is a physical building that holds all the multiplexers and exchanges. So how do we do those the multiplexer? How do they work? One of the ways they can do this is with a frequency division. So in this, it's a method of keeping calls on the same wire but on individual frequencies. So again, we call frequency division multiplexing. You'll see this abbreviated FDX or FDM sometimes, FDX or FDM. And what we're doing on this is we'll say this is a wire, and then here we may have a bunch of frequencies on the wire. And each frequency would have its own, each signal would have its own frequency on that wire. So in this case, you'd have 3 different frequencies on that wire. In fiber optic cable, it might be 3 different light signals. Again, light just being another form of frequency. In circuit switching, we dedicate a single pair of cable from an end to end. So from building to building. So this can get quite expensive at times, but some people will actually pay for it. Some companies will. It's rare. With packet switching, there's no reason to do the circuit switching anymore, but sometimes you may find companies that will do this. So in this case, you're going to have a building here, and this could be in Las Vegas, and maybe you have another building in Los Angeles, or say North Las Vegas. How about something a little bit closer? You could do this across country, but so North Las Vegas, and then you come to your telephone company, and they actually pull in a pair of cable. This is just nothing but vanilla shielded twisted pair of cable, and it goes from there to they have their own CO, and that pair of cable is dedicated to your building, and they get to this. That is the CO. They get the central office. They pass that circuit to another pair of cable. They run that circuit to a new CO, and then the last mile they take another circuit from or another pair of cable from there to your new building. So it is you're actually leasing a pair of cable all the way through. Now remember, an amplifier is a device that is used to boost a signal. Now remember, the amplifier, it boosts the signal, but also boosts noise. So if you have a lot of noise in the circuit and you amplify the circuit, all the good traffic along with the noise is going to be amplified along with the signal. This is typically used in analog circuits. A repeater, on the other hand, it receives a signal removes the noise, and retransmits a clean signal. At full strength. The last mile is the cable from your building to the central office. When we talk about central office, we're talking the central office of the telephone company, not your central office. The CEO belongs to the telephone company. So the last mile, you've got your building in here. This is your building. This cable goes from there to a central office, and this they call the last mile. Because this circuit might go through several COs before it gets to your other building. So this is you and your other building. And we made a satellite office or something like that. And again, you go. This is also a last mile. This is the last mile for this building. This is the last mile for this building. This is not a last mile. DS0, and that is DS0. This is a 64 kilobit per second speed or bandwidth. This is the minimum bandwidth needed for a voice signal. Modem. It's a device that converts digital signals to analog for transmission on the plain old telephone system. Get used to that term, POTS. Plain old telephone system. And then conversely, it also takes an analog signal from the telephone system and converts it to digital signal to get to your equipment. A T1, or sometimes you see just like that, T1 circuit, is 1.544 megabits per second. It's got 24 64 kbps or kilobits per second channels, and these are time division multiplexed. In a time division multiplex, you have a circuit, a wire, if you will. Remember we talked about frequency division multiplexing? Well, in time division, what we do is one signal gets so much time, then another signal will get so much time, and then another signal gets time, and another signal will get time, and then we go back to our original, and they share bandwidth on that circuit given time. Time goes that way. So it's 24 64 kilobit channels. It's 1.544 megabits, and we have one channel for framing. So 25 channels, 24 are usable. So we have a T1 circuit, or T1. Sometimes we put the dash in there, sometimes we don't. And this is, again, we specified 1.544 megabits, and with this 1.544 megabits, again, 24 DS0 channels. We have a T3 circuit, which is 44.736 megabits per second. And actually, we should put here. And this is 672 DS0 channels. In Europe, they don't use the T standard, they use the E standard. It's similar to the T standard. So with the E1 or E1 circuit is going to be 2.048 megabits per second, or 32 DS0 channels. And an E3 circuit was going to be 34.368 megabits per second, or it's 512 DS0 channels. Remember, DS0 is 64 kilobits per second, which is the minimum needed for a voice call. In the US, we have a synchronous optical network. This is made out of fiber. And we refer to that as Sonnet. In Europe, they also have a fiber network, and they call it a synchronous digital hierarchy. Or SDH. These are both fiber optic transports. They're high speed. And long distance. In here, speed is measured in optical carrier using the optical carrier standard, or OC standard. So here an OC1 is 51.8 megabits per second, and OC768 is 39.8 gigabits per second. So to calculate bandwidth, OC system. You're going to multiply the OC number, so 1, 2, 768 times 51.8. So everything's a multiple of 51.8. And as an example, of course, you see the OC1 and OC768, but we have an OC3, or common bandwidth is 51.8 megabits per second times 3, and that's equal to 155.52 megabits per second. Another fiber optic standard we have is the dense wave division multiplexing, or DWDM. And this is a scenario where a single fiber cable carries multiple signals. A lower cost version of the DWDM is the coarse wave division multiplexing. Or CWDM. Again, this is just a low. This is just a low cost version of DWDM. So packet switching. Packet switching technologies. Up to now, we've been talking mostly about circuit switching, or something similar to circuits. So we're dedicating a piece of cable from your building to the CO, from the CO to the other CO, and that CO to another building. So you're basically a circuit to the entire path. The disadvantage of a circuit switch if there's a cable break, redundancy is not inherently built into the system. So in packet switching, redundancy can be built into the system because we're not dedicating a circuit from building 1 to building 2 to from the building 1 to the CO, from CO to CO, from CO to building 2. What we're doing is we're going to take our signal and we're going to break it into packets and send those packets through the network. So if there's a redundant architecture in place, so we'll say you have something like, here's your building. Sorry about that. So here's your building. It connects to a central office. And there might be multiple central offices. In fact, there are in most cities. And something like this. And you've got a second building down here, another campus. If we take these things and split them into packets, you send one packet going this way to get to the building. The second packet can go this way to get to the building. So if there's a cable break here, the third packets, noticing the equipment will notice a cable break and route it down this way. So that, again, packet switching. Very similar to what we do with an Ethernet, Ethernet frames. These are just called packets. In fact, some of them are called frames. So let's take a look at packet switching technologies. The first one is frame relay. this is again, we allow many signals to be transported on a single port. And what we typically do here, it's kind of a hub and spoke. So you might have your corporate office, at one location, a bunch of small satellite offices. These small satellite offices have bandwidth requirements, and it might be fairly modest. We'll say it's a T1 or something, or 700 megabits or 300 megabits. They come into this frame relay cloud, and then you have just one high-speed pipe from your corporate office to the high-speed frame relay cloud. That's a frame relay cloud. And then each of these other circuits are relatively modest in terms of performance. Frame relay is being phased out in term and being replaced by MPLS. Asynchronous transfer mode or ATM. This allows for high-speed connections over fiber or Cat5 cable. And the one thing about ATM, rather than using frames or 1500 bytes, whatever, they use cells of 53 bytes for transmission of data. 53 bytes is very fast at switches. MPLS, actually multi-protocol label switching, MPLS. This is a relatively new thing. It hasn't been out as long. Frame relay's been around probably 25 years. ATM probably about the same, maybe a little longer. T1s and T3s have been around since telephones were started, so we're talking back in the 40s. MPLS is relatively new, probably been around since the early 2000s. And this is this is a technology replacing both frame relay and ATM. It inserts between layers 2 and layers 3 of the OSI model. Layer 2 and layer 3 of the OSI model. But so what we've talked about so far early on, Ethernet technologies and LAN technology, T1, ATMs, T3s, and MPLS are WAN technologies, wide area network technologies. So we've had networking, LAN, this next section is going to cover metropolitan area networks. MAN. In metropolitan area network technologies we're going to use, we have dial-up. Believe it or not, it is still used. In dial-up, we're going to be talking, we refer to as the PSTN. This is the public switched telephone network. Also known as POTS, plain old telephone system. But PSTN is a little bit more accurate because it is a switched network, where POTS was more of an analog network. The other technology we have, and with the modems here, we're probably talking 56K. If you hear the term baud, BAUD, that is the term you're going to hear within dial-up modems, PSTN. Again, baud. The other one we talk about, ISDN, Integrated Services Digital Network. I'm sorry. And up to here, we're not talking speed, a lot of speed here, but maybe 128 megabits to 1.54 megabits per second. If you hear the term up here under the PSTN, here you can hear the term modem. In ISDN, you're going to hear the term terminal adapter. So if you ever hear the term terminal adapter, we're talking ISDN. There are two ISDN technologies. The first one being called Basic Rate Interface, or BRI. In this one we have what are called two bearer channels, or two B channels, and they are BEARER channels, and one D channel. The total bandwidth you're going to get for the usable bandwidth is 128K kilobits per second. So again, not a whole, not real fast. So basically, two telephone calls simultaneously. But if you're working with really old technologies, sometimes call centers will use these for people to work at home when they've got the old green screen technologies for bandwidth isn't an issue. And you can take a phone call. You'd have one of those BRI circuits, one of the B channels dedicated to a phone, and the B channel dedicated to a computer. PRI circuits, they're still used actually a little bit more often than people would like to talk about, but this is the primary rate interface, PRI. In a PRI circuit, we have 23 B channels and one D channel, giving us a total bandwidth of 1.544 megabits per second. That looks a lot like a T1, doesn't it? Then that's basically a T1, but in this case, it's pretty much dedicated for phones, where a T1 can be used for both phones and data. PRI circuits largely are used for telephones anymore. Next we have the digital subscriber line, or DSL. Some people who have DSL hate it, other people love it. It is a digital technology. It's used by telephone companies to provide internet access to homes, and it's used by corporations. Actually, there are multiple types of DSL, and some of the DSL circuits can be used by corporations to provide internet access for corporations, or VPN access, that type of stuff. So we have two versions of DSL. The first one is symmetrical. Or symmetric DSL. And you'll see this one called SDSL. And the second one is asymmetric DSL. Or ADSL. SDSL is used largely by businesses. ASDL is largely by homes. SDLC, SDSL. These circuits have the same up and download speed. Or bandwidth. Typical performance here is 128 kilobits per second up to 9 megabits per second. So again, 9 megabits per second is not shabby, especially with up and download speeds. The ADSL circuits have different up and download bandwidth. Something typically here, you might get a 1.5 megabits per second download, and maybe a 1 megabit per second upload. And here's the one big issue with distance with DSL circuits. There's a maximum distance from the central office to the DMARC, or the customer location, is 3.4 miles. And the further you are from that central office, the slower the performance is. And by the way, keep that in mind, that's 3.4 miles of cable run. That's not 3.4 miles straight line distance. So you may have a central office here, but the cable runs this way, and before it gets to your office. And that distance from here, measured all that, is has to be 3.4 miles. So you might be, and then the other thing, the real kicker is, central offices aren't spaced evenly through your town. You can be literally within half a mile from a central office, but that's not the central office that services your house or your building. So keep that in mind. This is a circuit that telephone companies love to use. It's well designed for the most part. It's easy to install, easy to manage, but at the same time, performance does vary quite a bit depending how far you are from that central office. And again, it's only 3.4 miles, about 18,000 feet of distance. I'm sorry. Yeah, I think it's 18,000 feet from the central office to the your location. And the further you are from that central office, the slower it's going to be. Next, we're going to cover our next communication technology, and this is broadband cable. This is typically what in Las Vegas Valley it's given out by Cox Communications. There are other companies, Verizon, AT&T, even Google in parts of the country do this. The speeds are typically between 500 megabits to 200 megabits per second. They are getting a lot faster in many areas. Cox, I know you can actually pay, I think, for up to 500 or 1 gig per second here in Las Vegas. But typically at 200 megabits is not unusual. It is asynchronous by nature, and this means your upload speed to the internet is slower than your download speed. Again, download speed's what's coming to you, so if you're downloading YouTube or Facebook, that's coming at you at 200 megabits per second, but your ability to send files up to the internet, that's significantly slower. 5 megabits is unusual. This technology does run over a coaxial cable. If you've heard of Google and even Verizon now, they're starting to actually run fiber to homes, but right now it's still predominantly coaxial cable. The protocols used, actually the protocol used, it's not protocols, it's just one protocol, and it's called DOCSIS, or Data over Cable Services, or DOCSIS, like I said, DOCSIS. Next we have satellite. These are usually in remote areas. There are two types of satellite. We have one way, and here we can typically download via satellite. Your upload is using an alternative method. Probably your PSTN. Your PSTN is your public switch telephone network. And then we have a two-way communication, or two-way satellite. And this is your upload and download are done via the satellite. And fiber is what we're talking here. Again, this typically, if you look at AT&T and Verizon, they're starting to run this stuff. Verizon calls it FiOS. And in this case, they're running fiber to your homes. And Google's also doing this in parts of the country now. So even we've talked about this before. I got a definition, and we called it an extranet. We talked about VPNs. We actually refer to an extranet, and an extranet is where a company allows remote users access some part of its private network, usually for employees. So employees or contractors. HR, timesheets, email. Remote access, we're typically talking about someone coming into your home, accessing your business from home. Now we can use these with contractors, accessing your business from their offices, etc. And there are a couple ways we can do this. One is dial-up to the internet. Typically this uses the point-to-point protocol, and it's you dial up to an ISP. Very rare here in the United States. Just dial-up's not used very much anymore. We have private dial-up. And here you're going to connect from the remote location directly to the company. For this, you're going to need a remote access server, or RAS. Again, very, very rare that we see that anymore. Dial-up is just not used. There, at one time, in the 90s, early 2000s, it wasn't unusual to see banks and banks of PCs that supported dial-up. How else do you get remote connectivity to your company? VPN. Now, a lot of times what we do when we VPN in to work from your home in, you now have a connection to your home, but how do you, or from into the network, but how do you access resources? And one of the ways we access resources is we do a connect to a remote desktop using the Microsoft's remote desktop protocol. And this is on TCP port 3389. You will hear this abbreviated RDP. That's the remote desktop protocol. You can also do a virtual network computing. Or VNC for short. And again, this is also like your remote terminal, but it's a remote access to a workstation, or a virtual workstation. The difference, the first one being remote access to a physical workstation or physical desktop. This is a remote access to a virtual workstation. And again, we use the same ports, TCP 3389, because we're using RDP. So what other technologies do we have in this area of wide area connectivity, or connectivity from your corporate office to the outside? One is voice over IP, VoIP. Again, this is where you use your IP network to make voice calls. With VoIP, we have several different standards. those. One is the real time transport protocol, or RTP. We also have the session initiation protocol, and this is extremely common. RTP is used quite often, and in many cases you'll see RTP and SIP, session initiation protocol, used together. And SIP uses the H.323 protocol. They kind of use each other at that time when they're using SIP. H.323 is not unusual to find with it. Your real-time protocol defines the types of packets used on the internet. SIP, or H.323, these protocols do session initiation, setup, and delivery of VoIP sessions. Both protocols use RTP. So RTP has to be running, and then SIP or H.223 run on top of it. SIP uses ports TCP 5060 and 5061. Where H.323 uses TCP port 1720. The last two protocols we refer to are Skype and about Skype. This is not compatible with other VoIP standards. It is a peer-to-peer network. So peer-to-peer, we're talking, you got a handset at one location. For peer-to-peer, we're talking, you get a handset at one location, and it's talking to another location. And again, it's a peer type situation. This handset here, you can dial this handset directly. They don't have to go through any kind of central office or PBX type of environment. And the Skype uses its own proprietary encryption system. And the last one we will discuss is streaming media. With streaming media, in this case, we're talking, we're using the real-time streaming protocol. Or RTSP. RTSP uses the port TCP 554, and this also requires the use of RTP. Whoa, what did I do? That is it for Chapter 13. So we'll go over Chapter 14, wireless. I'm going to probably break wireless up into several videos. It's not that it's a long chapter, but it's very important for the test.